Yesterday we have studied about resonance in LCR series circuit. So we have said LCR series circuit is that electrical resonance when the circuit power factor becomes unity. That means cos phi is equal to 1. When the circuit power factor becomes unity, the impedance becomes minimum and the current becomes maximum. So this is attained when XL is equal to XC or VL is equal to VC, right? So this can be achieved by changing the supply frequency, the frequency of the supply voltage. All this is explained. Today I am going to explain you what are the uses of LCR series resonance circuit. So I have basically told you that this kind of circuits are used in tuning purposes. Tuning means radio tuning, television tuning, etc. We can use this LCR series resonance circuit, right? So this is one of the very important use of resonant circuit is what is called radio tuning and television tuning. So in this, you see, this is the input signal is coming from the antenna, and this is coupled with an LCR series circuit. LCR series circuit like this, and this that means this will induce an EMF E across L. That is E is E, and EMF is induced in L, right? Of the series circuit, and as the circuit has a very high value of quality factor, then the voltage across C becomes very high. That is equal to VC is equal to Q into E, which is very much very much greater than the induced EMF E. So hence the amplifier will get a very greatly amplified signal. It will get a very high magnified signal. The amplifier will get. This is an LCR series circuit. LCR series circuit is used for this one. You will see that this R is actually the what is called inborn resistance. R is actually not it is not a separate resistance. That resistance is actually associated with the inductor only, right? When you look at this one, you will feel that this is a parallel LC circuit, but this is not parallel because there is no separate voltages given to L. So the voltage L gets is only an induced EMF. That induced EMF will be in series with the C. Therefore, this is only a series LCR circuit. At resonance, the voltage across C becomes very high because we had to tune also. This is variable capacitor. We have to tune the value of the capacitor C is so adjusted that then the voltage becomes very high across it through the capacitor. Why that? Because we are changing the value of a capacity at a particular stage. The capacitance VC becomes equal to VL. That means the XL becomes equal to XC, and the circuit becomes resonant. Hence the voltage becomes very high, current becomes very high, and voltage across the capacitor becomes very high. That is many times greater than the induced EMF in the coil L, right? So an amplified signal is also that a signal of very strong and highly increased signal the amplifier gets, and we can tune the programs in a proper way. So this is what is called the applications of LCR series resonance circuit, and it is used for what? Used for tuning, radio, television, etc. Am I correct? So for any this kind of circuit to work, there must be a range of frequencies. Range of frequencies with which this kind of circuit work is called bandwidth. Bandwidth is a final frequency minus initial frequency. So bandwidth of such circuits are called BW is equal to F2 minus F1. So there is a range of frequencies for which this kind of circuits will work very effectively. So bandwidth is equal to F2 minus F1. So bandwidth is nothing but it is the bandwidth of a series resonant circuit is the range of frequencies over which the circuit current is 70.7% of the current at resonance. At resonance, what will be the current in the LCR series circuit? And bandwidth is that range of frequencies for this range, between this range, the current will be about 70.7% of the resonant current. That means what will be the maximum current at resonance. And the 70.7% of the current it will be there when these two frequencies, this frequency range F2 and F1 are to be used. So bandwidth is the range of frequencies for which over which the current in the circuit is 70.7% of the maximum current at resonance. We can also show that the quality factor Q is equal to Q factor. Q is a quality factor. Q is equal to F2 minus F1 divided by F2 minus F1. That means FR divided by FR means the resonant frequency. That means the frequency at which resonance takes place. FR divided by BW we can write. That means FR divided by F2 minus F1. So this way also we can calculate the quality factor. So quality factor is a very important thing. So quality factor is a physical meaning you have to understand. The definition of that you understand. Quality factor is only a physical quantity having no unit at all, right? This is equal to, right? The voltage across the capacitor inductor divided by the applied voltage. So quality factor is very important. This kinds of circuits must have very high value of quality factor, right? Next thing what I want to speak about is parallel LC circuit. We only nominal idea about that, and also I'll explain and we'll finish today's classes, right? Okay. Parallel LC circuits, oscillations in parallel LC circuits. So very simple this is. So what I am drawing here, it is a capacitor, right? So this is an inductor also here. This is an inductor also here, right? So it is coming here like this. And now this is connected to a battery, right? And it is also coming here. Okay. This is a battery. Right. Now this is a key. Key is first connected with the battery. This key is first connected. This is a floating key. First of all, sometimes it is connected to this the battery circuit. Sometimes it is connected to the inductors. This is L and this is C and this is a battery B. So this is a LC parallel circuit. L and C are connected in parallel. First of all, what do you do? This capacitor is connected to the battery circuit. So within no time, in a very small instant of time, what do you see? The capacitor gets charged. Capacitor charged means this plate becomes positive and this plate becomes negative. Once the capacitor is charged, this is connected to the inductor. Now this is an LC oscillator circuit. So parallel LC circuit is an oscillator circuit. Oscillator circuit means the current will move to and fro. That means the charge will oscillate within the circuit. That is why this is called LC oscillator. In a parallel LC oscillator, an inductor and a capacitor are connected parallel. First of all, the capacitor is charged to full voltage V, and now it is connected to an inductor. Now what happens? The capacitor starts discharging through the inductor. So this is the condition what we talk about LC oscillation. So LC oscillation is very simple. First of all, so this thing I am writing in with different conditions. Okay, I am drawing this figure, right? Okay, this is an inductor, and this is a capacitor. Capacitor is now at present is fully charged. This is positive and this is negative. And it starts to discharge the inductor. Discharge the inductor means the positive charge of this capacitor starts moving through the inductor. That means the current starts flowing through the inductor. Through the inductor and current passes, the magnetic field inside increases. That means the flux variation takes place, right? It gradually increases. So due to which what happens, the flow of charge is always opposed by the inductor. So the flow of charge gradually increases and it becomes maximum, right? When the current through inductor becomes maximum, the flux inside also becomes maximum. So a maximum flux is increased through this one, right? This is the first condition. We don't write the marking here. And next time I'm going to draw this is the condition there, right? So the current through from the capacitor starts discharging through the inductor. When current through inductor is maximum, the flux through this will be maximum. Flux can be represented by this dotted lines like this. When the flux through this one is maximum, what happens? The charge in the capacitor is completely washed off because the charge from the capacitor is gradually flowing through the inductor. Magnetic field inside gradually increases. And when the magnetic flux or field inside the inductor or the coil becomes maximum, the charge in the capacitor totally vanished. There is no charge. So when there is no charge, the magnetic field inside will be very much maximum. Now, actually, what happens is that when the capacitor was fully charged, the energy was half CV². Right? Now it is discharged to the inductor, then magnetic field inside gradually increases. When current through that increases, when current becomes maximum, the energy inside is also maximum. That means this electrostatic energy will be converted into magnetostatic energy. That is when by U is equal to half Li². Already taught to you, right? Now the current through the inductor is maximum. That means the electrostatic energy is converted into magnetostatic energy. So the magnetic energy inside a coil is given by half Li². When the magnetic field or the flux is maximum or the energy is maximum, the capacitor is fully discharged. Right? When the capacitor is fully discharged and there is no charge to come to the coil, the flux starts decaying. Decaying flux will induce an EMF inside the coil that will charge the capacitor oppositely. That means the second plate becomes positive and the first plate becomes negative. That also we'll see. So that is this diagram. Now the inductor is fully decayed and this is the situation. So this becomes positive and this becomes negative. There is no field. Again, what happens? The magnetic flux inside or the magnetic energy inside of the coil is totally converted into again half CV². You have seen one thing, what is happening. There was positive charge. All the positive charge has gone to the other side. This is what is a half cycle is over. Right? Because this is an oscillatory circuit. Because oscillator circuit is a circuit that can convert DC current to AC current. So this is the first half. In the first half cycle, all the positive charge of one plate has been turned to that has gone to the second plate. So now this is positive and this is negative. So now again the capacitor is fully charged and the magnetic field inside the coil is totally empty. Energy is changed from half Li² to half CV². Now this charged capacitor, fully charged capacitor is now again ready to discharge the inductor, but in the opposite direction, right? What happens then? Then that diagram I am drawing like this, okay? Now this is again discharged like this. So that means the current flows in the opposite direction. Gradually the current to inductor increases, and when becomes maximum, again half CV² is converted to half Li², then the magnetic flux inside the coil becomes maximum. Current through the coil when becomes maximum, the capacitor is fully discharged. Am I correct? So this is the situation. So now in this case, the electrostatic energy of the capacitor half CV² is fully converted into half Li² magnetostatic energy, right? Now this current is maximum and magnetic field inside, magnetic flux density inside the coil is also maximum, right? Now there is no charge to come from the capacitor, again the magnetic flux inside the coil starts decaying. Magnetic field starts decaying. Decaying magnetic flux will induce an EMF in the coil that will charge the capacitor oppositely. That is this condition. That is again, so the capacitor is getting charged as it was, means this becomes positive and this becomes negative. This is the next half cycle. In the first half cycle, positive charges are flowing from one plate to another, and the next half cycle, again, the charge is coming. This is what is called full cycle. So this is how oscillation takes place in a LC oscillator. LC oscillator is parallel LC oscillator. Why it is called parallel LC oscillator? Because an L and C are connected parallel. First, the power is given from a battery. Energy is actually given from a battery. That means DC current was given to the capacitor, and that starts discharging and oscillation starts. So this circuit can be said to be an oscillator. That means DC current can be converted into an AC current. So this is what is the simple idea about LC oscillator. So in LC oscillator, what is happening is that always there is loss of current through an LC oscillator, because this charge is flowing through the wire only, and in the wire always there is a resistance, right? Resistance losses there. In the inductor there is a resistance loss, because the inductor is made of a copper wire. So inside the inductor there is an inborn resistance. Is the induction effect also there, and also resistance effect also, right? So actually separately with an inductor, resistance is not marked, not necessary that. Why? Because inside the inductor itself, induction effect is opposition, inductive reactance is also there, and also resistance is also there. Why that? Because inductor is made of a wire. Wire has copper effect, right? Copper loss means heating loss. So inductor, through the inductor, when current passes, due to resistance, some energy is lost. Therefore, the AC EMF we are getting is not having a constant amplitude. If there is no loss, if there is no loss of energy, then this is EMF and this is time, and this EMF obtained will have the same amplitude every time. But in an LC oscillator like this, once a capacitor is charged and it is made to discharge an inductor, oscillation takes place. Right? If there is no loss of energy means loss of energy takes place in two conditions. I said one is the resistance loss. Resistance loss is the resistance over the inductor. Why inductor dissipates some energy? Because inductor is made of a wire. Wire has resistance. That is what is the resistance loss. Other losses that are called dielectric loss. Between the two plates of a capacitor, a dielectric is kept there. The dielectrics also will be charging and discharging time to time, due to which also some energy will be lost. So these are the two losses mainly seen in LC parallel circuit. So due to that, what is happening is that the EMF obtained in this LC circuit is not having a constant value of amplitude. E is always not a constant amplitude. This kind of EMF we must get, sinusoidal EMF we will get. But most of the time, what is happening is that the amplitude of the EMF goes on decreasing and finally becomes equal to zero, though the frequency always remains a constant. So this is the condition. So first of all, in the earlier time, the amplitude is a very high value, then goes on decreasing, like this, and finally becomes equal to zero. Because why it becomes equal to zero? Because of two losses. One is called resistance loss, and other is called dielectric loss inside a capacitor. Where is the resistance loss? Resistance loss is inside the inductor, and dielectric loss is inside the capacitor. So that is why we say that though the frequency of the voltage in the voltage given by this LC circuit remains a constant, but its voltage, the amplitude goes on decreasing and finally becomes equal to zero, right? If we have a method, a suitable technique, if we use, with the help of which, if we can feed back the energy lost in every oscillation, then the maintained oscillations can maintain AC EMF can be obtained, having a constant value of EMF. Otherwise, this is the damped oscillation. Damped oscillation means a oscillation of EMF with its amplitude goes on decreasing. This is damped one. This is maintained one. For maintained oscillations, what we have to do, every instant, what all amount of energy is lost in the circuit, either due to resistance loss or due to dielectric loss, that has to be fed back to the circuit, and the amplitude can be maintained and can have a constant EMF, EMF with a constant amplitude we can obtain, right? This is about parallel LC oscillator. So LC oscillators are also is called oscillator because this converts DC current into AC current. AC current is an oscillating current. So today's topic, only this much I am teaching. The other day will come with a new topic. Till then, bye bye. Thank you very much.